In these three examples, we want to determine each partial sum. So first we need to figure out what type of a series we have. Are these going to be arithmetic? Are they going to be geometric? Or perhaps are they neither? So looking at example A, it says we want to find S sub 6. So this means we're finding the sum of the first 6 terms for the sequence that starts out with 2 and then 6 and then 18. So we want to identify the pattern from 2 to 6 and then 6 to 18. And assuming that that pattern continues, we want to determine the sum of the first 6 numbers without actually adding all of the individual 6 terms together. So the pattern here appears to be that we are multiplying by 3. So if we are multiplying by 3 repetitively, that makes this a geometric series, and we know that r is equal to 3. So we have a nice formula for a sum of a geometric sequence of numbers, which is what we call a geometric series. And that's going to be S sub n is equal to the first term, a sub 1, times the quantity 1 minus r raised to the n power, all divided by 1 minus r, where r is our common ratio. So in this case, if we're looking for S sub 6, we want to add the first 6 terms. The first term is 2, times the quantity 1 minus r is 3. We'll raise that to the 6th power, since we're looking for n is equal to 6, all divided by 1 minus 3. And at this point, you're welcome to grab your graphing calculator and enter this expression in. Just be very careful with parentheses. Some common mistakes I see occasionally. Some students make the mistake with the exponent of the 6 and accidentally put it on the outside of the parentheses. So be sure you don't do that. I think that sometimes happens because many students have studied compound interest and the compound interest formula here. And if you haven't studied this yet, then completely disregard. But if you have studied compound interest, you'll notice that that exponent is on the outside of the quantity of the parentheses. So I have seen some students get confused there. Be sure that the 6 is inside the parenthesis. The 6 only applies to the 3. And it looks like this will equal 728. So again, this would be the same as adding up the first 6 terms of this geometric sequence, and we would end up with 728. But we're utilizing the formula rather than brute force of actually adding together the 6 terms. Now our next 2 examples are in sigma notation. So the Greek letter sigma is telling us that we want to add up all of the terms. But we need to identify if the general rule here is going to create an arithmetic sequence of numbers or a geometric sequence. And in this case, because we have -2 raised to a power, that's our signal that we are going to get a geometric sequence. Now we could actually go ahead and plug in 1, and I'll actually show that. If we were to plug 1 in, because it's telling us at the bottom here that k is equal to 1, so we want to start by substituting 1 into our general rule. We'd have 8 times -2 raised to the 1 minus 1 power, which is really 8 times -2 to the 0 power. -2 to the 0 power is just 1, so we would end up with 8 as our first term. A sub 1 equals 8. Now if I did this a second time, to find the second term, and I substitute in 2, we'd have 8 times -2 raised to the 2 minus 1 power, which is the same as 8 times -2 to the first, which would give me -16. So this would show that the first term of the sequence is 8, and the second term is -16, and then we would continue on. And you can see here that to go from 8 to -16, we multiply by -2. So if I multiply by -2 repetitively, that's telling me that my ratio, my common ratio, is -2. Now I wanted to show you this worked out longhand, one time. But now that you've seen this, I hope you can come up here and look at your general rule and realize we should have known that r was equal to -2 because -2 was the base. In this exponential expression, we have -2 as the base, and it's raised to the exponent or the power of k minus 1. So that base value is going to be -2, and that's going to be our R value. So once you recognize that, it's really not necessary to write out the first several terms to find your R value, although you could if you didn't recognize that initially. So I'm going to go ahead and back up. I don't really need this work for my second term, so I am going to erase it. However, I am keeping my work for the first term because if you look at your general sum formula, remember, notice it requires that we know the first term. So that's going to be necessary. Now, we need to know how many terms we're adding. And if we're starting at k equals 1 and summing until we substitute in 7, from 1 to 7 is a total of 7 terms. So in this case, n is going to equal 7. Essentially, we will have 7 terms that we'll be adding together. So now let's go ahead and find the sum of these first 7 terms. So utilizing again our sum formula here for a geometric series, the first term we found was 8 times 1 minus the R value we said was -2, so be sure you have R in parentheses. That'll be -2 raised to the 7 power, since n is equal to 7, all divided by 1 minus -2. Now here, I have to caution you because when you grab your graphing calculator, it's going to be incredibly important that you're careful with parentheses. So you will want to enter it exactly as I have it written here, which means if you're working with a TI-84, you're going to want to go ahead and create a vertical fraction. Be sure you have parentheses here, and then you also need to make sure that you have the parentheses around the -2, just exactly as we have written here. If you're working on a TI-83 calculator and you don't have the opportunity to create a vertical fraction, and your entry will look something like this, 8 times 1 minus -2 to the 7th power, and then you would have your division sign. It'll look sideways like this on a TI-83. Then be sure that you're putting the entire denominator in parentheses as well. So you would need an extra set of parentheses if you're on a TI-83. It would look like this. Otherwise, again, on the TI-84, be sure you're entering this as a vertical fraction. And of course, if you really wanted to simplify the denominator, you could do so. But I tend to just go straight to my calculator from here, and it looks like our sum should be 344. Now let's move on to this last example. So rather than actually substituting in 1 and then substituting in 2 so that we could see the pattern, I hope you can recognize it a little bit more easily now that we have 5 raised to a power. So that's telling me that it's a geometric series and R will be equal to 5. I'll be multiplying by 5 repetitively. I will go ahead and substitute in 1 for n. Remember, we're subbing in 1 because in the sigma notation, the index here is n equals 1. So that's telling me to substitute 1 in to find my first term. And 5 to the first power is just 5. So interesting on this one that the common ratio is 5 and the first term is also 5. Now summing, adding from n equals 1 all the way to 8 means we're adding a total of 8 terms this time. So n is equal to 8 when we use our summation formula. I need a little more room, so I'm going to scoot over. So our sum in this case of 8 terms, so this is a partial sum, will equal the first term, which is 5, times 1 minus the R value, which is also 5, raised to the 8th power, all divided by 1 minus the R value, which is 5. And you'll notice I put parentheses. I shouldn't be inconsistent, I'm sorry. I did put parentheses here around the 5. And as I look back on my previous example, on the first example where R was 3, notice here I did not put parentheses around the 3. When your R value is positive, you really don't need to have the parentheses around the R value. It's only going to be important when the R value is negative. So you can do that either way. And then let's go straight to your calculator, being very careful with parentheses again. and this is going to be a very large sum since we're multiplying by 5. It looks like 488,280 will be the sum of the first 8 terms represented by this geometric series, which is written in sigma notation.